Section 5-5 is on the mean value theorem and Rolle's theorem. The objective of this section is to use mean value theorem to find the point in an interval at which the instantaneous rate is equal to the average rate. And so it might sound like we're kind of taking a sidestep here from what we saw in the last section. The last section was on Riemann sums, but let me try to make this a little bit clearer for you in terms of what we are trying to do. In the last section, we talked about Riemann sums, and the Riemann sum was approximating definite integrals using rectangles. And we even said that if you were very careful on how you picked the sample point in each subinterval, that the area of the rectangle would be exactly the same as the area under the curve for that subinterval. And of course, if we did that for every single subinterval, then our Riemann sum would actually be the exact area under the curve. It would be exactly equal to the definite integral. That's our goal. And the question then became, how do we pick those sample points in order to make that happen? It turns out, although it might not seem like that on the surface here when we get into mean value theorem, but it turns out mean value theorem is that key for us. It tells us how we're going to have to pick our sample points. And so in the next section, section 5-6, we're going to combine those two, Riemann sum with mean value theorem, to get the exact area under a curve. That is the exact definite integral. All right, so let's take a look at mean value theorem. All right, here's the mean value theorem. The mean value theorem says the following here. If, first of all, f is differentiable on the open interval from a to b. Now, again, remember the open interval here is talking about the values of x between a and b, but not including a and b. So another way to write that would be that a is less than x, which is less than b. It'd be the same thing there. The second condition that you have to meet is that your function has to be continuous on the closed interval from a to b. We use square brackets to indicate a closed interval. You can see we use parentheses in the first condition here to indicate an open interval. And the closed interval from a to b means that you include the endpoints. Another way to write that would be a is less than or equal to x, which is less than or equal to b. It means the same thing. So if you meet these two conditions, you're differentiable on the open interval, you're continuous on the closed interval. And remember that we've already talked about in the last chapter the connection between differentiability and continuity. If you're differentiable, you automatically get continuity with it. So in other words, if you can show you meet the first condition, if you show that you are differentiable from a to b on the open interval, you automatically get continuity on the open interval. And then it comes down to just looking at the endpoints there, at a and b individually. Now, ideally, if we can show differentiability on the entire interval, we get both conditions in one step. So if we meet those two conditions, then the conclusion says there exists a point C on the open interval from a to b such that f prime at c, that would be the instantaneous rate that we were talking about in our objective there, is equal to f of b minus f of a all over b minus a, which that's an average rate. We were calculating those way back in chapter 1. So we're saying that at some point, our instantaneous rate, f prime at c, is equal to our average rate, f of b minus f of a all over b minus a. Let's look at a sketch of this to kind of help illustrate what we are trying to say with this theorem, or what this theorem tells us here. And let me just sketch a curve in here. Really doesn't matter what our curve looks like, but we'll call this our function f of x. And we'll pick some interval here, so let me say that this is a for us, and we'll say that this is b. And so that corresponds to 2 points here. I'll name these two. So this is a, f of a. And this point over here is going to be b, f of b. And the right side of this conclusion here, f of b minus f of a all over b minus a, is talking about the slope of a line, actually. It's the slope of the line that goes through these two endpoints that I just marked here. In fact, let me sketch that line here for us, or I'll try to sketch that. It's that line right there. The slope of that line is the slope that we're dealing with up there, that we're talking about. This is actually what we call a secant line, where it goes through 2 points on your curve like this. And the slope of it, of course, is equal to the difference in the y's over the difference in the x's. So that's just f of b minus f of a all over b minus a. That's this guy right here that we had in our conclusion. So it's talking about the slope of the secant line when they write that conclusion, or that's an average rate. So the conclusion guarantees us that there's some point C such that f prime at C, that's talking about the slope of our function at C, the instantaneous rate of our of change of our function at a point C, has to have this same slope of the secant line. So I'm going to have to kind of approximate where it's at, but I'm going to say that C must be somewhere about right here, and I'll try to sketch in the tangent line right there at C. So this is C. This guy right here is what we call our tangent line. And the way that you find the slope of a tangent line is you take the derivative of your function and evaluate it at some point, which in this case is C, and that tells us the slope of our tangent line. Which, again, if you look at our conclusion here, that's this guy right here on the left side. So again, the conclusion is basically saying that there exists a point C on the open interval from A to B such that f prime at C is equal to f of b minus f of a all over b minus a, or that's another way of saying the slope of the tangent line is equal to the slope of the secant line, or that's another way of saying the instantaneous rate at C is equal to the average rate from A to B. So there's several ways you could state that. All those mean the same thing here for us. So that's what the mean value theorem says. Okay, it talks about the existence of this point C. And again, that's the connection to Riemann sums that we need, is a way to come up with these sample points, which it turns out this C value is what we're talking about. All right, let's take a look at the conditions there for mean value theorem. They give you a sketch in the book with this these three sketches in there. And they illustrate for us the reason for the conditions of mean value theorem, why we have to have all the conditions that we've stated in there. So let's start over here on the left, which explains why you have to have the first condition in order for the conclusion to be true. The first condition, of course, for mean value theorem was that your function had to be differentiable. So if you look there on our sketch that they have there for us, they've got a cusp right here at C. So we definitely are not differentiable at that cusp, so we're not differentiable on the interval from A to B. And you can see that the problem that we're running into then is if you look at the secant line through A and B, that's this line that right here that they've got sketched, at no point in the interval from A to B is there a tangent line that has that exact same slope. And the reason for that is because of the fact that we've got this cusp in there. Okay, so I definitely don't know that the conclusion is going to be true or false without having this first condition met. All right, it is possible, by the way, you could have a cusp in your interval and still have the conclusion being true. Turns out for this example, it was not. But this illustrates why we have to have that first condition in order to guarantee the conclusion is true. Now look at the second sketch. The second sketch now, it's differentiable, so it meets the first condition. It's differentiable on the open interval from A to B, but it's definitely not continuous on the closed interval. You can see that over here at x equals a, we have this step discontinuity. Now because of the fact that we have that step discontinuity, you can again see the problem that we're going to run into. If I sketch in the secant line right here, you can see that there is no point from A to B where the slope of my tangent line at C is going to be equal to the slope of this secant line that I've got sketched. So again, that's why the second condition is extremely important, that we have to have the second condition met in order to guarantee the conclusion is true. Now again, I'll state, like I did with the first example, that just because I'm not continuous does not mean you can't have this conclusion true, but I don't know it's true unless I'm definitely continuous. All right, and the last example shows you what happens if we meet both conditions and why the conclusion is true there. You can see that in this example, I do have a cusp, but it's at the endpoint, so I'm not differentiable at A, but that's all right. I only have to be differentiable from A to B and not including the endpoints, though. So I am differentiable from A to B on the open interval. I am continuous from A to B, including the endpoints on the closed interval there. So you can see that I've got a secant line that goes through A and B just like that. And furthermore, you can see that I've got a point C where the slope of that secant line is the same as the slope of this tangent line. And that's what the theorem guarantees me. If I can show that I meet the two conditions, I can guarantee that, in fact, there is a secant, or there's a tangent line that's parallel to parallel to my secant line. The slopes are the same. All right, so let's take a look at an example. Take a look at example 1 here. Example 1 gives us a function, f of x is equal to x to the 1/3. And the question there says to plot the graph. We'll do that here in a second. It says explain why f satisfies the hypotheses of the mean value theorem on the interval from 0 to 8. So let's write down that interval from 0 to 8 as well. All right, so let's first deal with mean value theorem. Now, mean value theorem, I guess as you saw on the last slide there, we abbreviate that as MVT as a way we can abbreviate that for ourselves. And there's two conditions that I have to show that I meet in order to guarantee the conclusion is true. So they want me to show why I meet the conditions or the hypotheses of the mean value theorem. All right, so the first condition was on differentiability. And I had to show that I'm differentiable on the open interval from a to b, which is 0 to 8 in this case. So let's find the derivative of this function, f prime of x. It's just a power function, so use power rule. It's going to be 1/3 x to the negative 2/3. In fact, I'm going to rewrite that here. I'll leave the 1/3 out front, but x to the negative 2/3 can be written as 1 over x to the positive 2/3. I'm just rewriting that just so I think it's easier to see where this thing's undefined. What value of x can I not divide by there? If I plug in x as 0, this thing is going to be undefined. So f prime of x exists for all x not equal to 0 is what I have there. So it's only undefined, f prime is only undefined at x equals 0. So in other words, function f is differentiable for all x not equal to 0. I only need x's from 0 to 8, not including the endpoints there though. So I can state thus f of x is differentiable on the open interval from 0 to 8. If the derivative exists, that's what it means to be differentiable. Then I'm going to have differentiability on it for all x not equal to 0, but in my case I just have to worry about from 0 to 8. That's the first part of the mean value theorem, the first condition we have to show that we meet. The second condition, or the second hypothesis, is that I have to have continuity. Now remember, if I have differentiability, I automatically get continuity with it. So from what I've done in part 1 already, I already have continuity technically from 0 to 8, but I'm also going to get the right endpoint here as well. And I can say since f prime of x, oops, not f prime, but f of x, is differentiable on all x not equal to 0, and differentiability implies continuity, then f of x is continuous on the closed interval from, or not a closed interval, it's actually half open and half closed. It's from 0 to 8, not including the 0, but including the 8. Again, that's the part of the interval that I need to worry about, is only from 0 to 8. I don't need to worry about the rest of the domain of this function. But just from differentiability, I automatically get all but one point, the left endpoint. So we have to go back to our definition of continuity to figure out whether the left endpoint is continuous there or not. So let's go back to our definition of continuity at x equals 0. I'll put a question mark there because we're really trying to figure out whether or not we meet the conditions for continuity. Now, remember, there's 3 parts to the definition of continuity. The first one is that your function has to exist. So I'm going to write that as a question. Does f of 0 exist? It's really a question we're trying to answer. And so I can plug in 0 into my function. Remember, our function is the cubed root function, so that's 0 to the 1/3, which of course is 0. So as long as I plug in a number and I get a number out, then that means it exists. So we can write yes here. 1 down, 2 to go. The second condition for continuity, or the second part of the definition, I'm going to write it as a question again, is does the limit as x goes to 0 of f of x exist? All right, so if we take the limit as x goes to 0 of x to the 1/3. Now again, we can find a limit by using substitution. If I plug in 0, I get 0 to the 1/3 power, which of course is equal to 0. So that means the limit exists. We get some number out, so yes, the limit exists. That's 2 down, and actually, the third part of the definition of continuity actually uses those previous 2 values there. So the last part is to check to see does the limit as x goes to 0 of f of x equal f of 0. And obviously you can see from the work we've done above there, both of those were equal to 0, so yes. All right. So thus, we can conclude that f of x is continuous. Of course, this just gave us the endpoint x equals 0. We've already stated that up above that we had continuity from 0 to 8, not including the 0. So this gives us continuity on the entire closed interval from 0 to 8. Okay? So we've met the conditions for mean value theorem. The next part of this says to find the value of x equals c in the open interval from 0 to 8 at which the conclusion of the theorem is true. So remember, the conclusion of the theorem says this: therefore, oops, spell that correctly. Therefore, by mean value theorem, there exists a point C on the open interval from A to B, but I'm going to write it as from 0 to 8, such that the following is true, that f prime at C is equal to f of B, that's f of 8, minus f of A, which is 0, all over B minus A, that's 8 minus 0. Okay? So the question is, can we find this value of C now? Let's first of all evaluate f of 8 minus f of 0 all over 8 minus 0. Well, f of 8, the function here is the cubed root function. The cubed root of 8 is 2. We've already evaluated what f of 0 is from our check of continuity there. We got 0 out of that thing. All over 8 minus 0. So that's 2 over 8. That's 1/4. So basically what I want to do is I want to find where my derivative over here on the left is equal to 1/4. That's what we're really trying to solve here. So we've already found the derivative actually from above there. Let me just scroll up there so you can refresh your memory here. We did that in showing differentiability. F prime of x was equal to 1/3 x to the negative 2/3. So f prime of c would be 1/3 c to the negative 2/3. I'm trying to find out where that's equal to 1/4. So here's the equation that we need to solve to find out c. You could use your calculator to do this. You could graph this function on the left side, graph the function on the right side, the 1/4, and find where they intersect. You could use solver to do it. This one isn't too bad to do algebraically, so I'm just going to go ahead and use a little algebra to do that. Move the 1/3 to the other side, and you get c to the negative 2/3 is equal to 3/4. And now to solve for c, remember I need to raise both sides to the same power. And the power that I need to raise it to is actually the reciprocal of this exponent over here. I want to raise it to the negative 3/2 power. So that when I raise c to the negative 2/3 to the negative 3/2, those exponents, of course, multiply to give me 1. I'll end up with c to the first on the left side, which is what I want to know. What does c equal? Turns out it's equal to 3/4 raised to the negative 3/2 power. I don't think I would worry about finding the decimal approximation of it, but you certainly can do that. I'm going to go ahead and do it here now, but this is sufficient to leave it in that form. But let me go ahead and punch that in our calculator. So if we take 0.75 and raise it to the negative 1.5, 3/4 is 0.75, negative 3/2 is negative 1.5. We get 1.53, I guess I'm going to say 1.5396. I'll put an extra decimal on there for us. 1.5396. And that definitely is in the interval from 0 to 8, so that's the number we're looking for. Now, it could be that there's more than one value that this happens at. In this case, we just have the 1. Okay. And it says, show your graph, show on your graph that the tangent really is parallel to the secant line. All right, so to do that, let's actually come up with the equations of our secant line and our tangent line, and plot all three of these together. So, let me maximize this. So let's start with our tangent line. So for our tangent line, we need a point and we need slope. I actually have the x value for my point here, actually. I just need to find out what the corresponding y value is. I just need to find out what f of c, or f of 1.5396 is equal to. And I've already got the slope there, f prime at 1.5396. Remember that I set my derivative equal to this 1/4 up here. I said f prime of c has to equal 1/4. So I already know the slope there is 1/4. So there is really just one value I need. I need the y value, and then I'll be able to use my point slope formula to find the equation of this. So let's go to our calculator and have it calculate this value for us. So I just need to take the cubed root of this value. Remember, our function is x to the 1/3. I'm going to calculate this value here raised to the 1/3 power. And we get 1.1547. 1.1547. And so there's my equation that I need. So I've got, there's the values I need. I got to write my equation here. We'll do that over here on the left. It's y minus y1 is equal to m times x minus x1. So it's y minus y1 is the 1.1547 is equal to my slope, which is 1/4, times x minus x1. That's the 1.5396. And if you want to solve that for y, that's going to be 1/4 x minus 1.5396. I'm going to add on the 1.1547. Definitely had to have a couple of extra decimal places on there just so that when we go to graph this thing, you get as good of a sketch as possible. And let's also come up with the equation of our secant line here. Our secant line, remember, goes through 2 points. It goes to the point at the 2 endpoints here. It goes through the point at x equals 0, and I got to find the corresponding y value, and x equals 8. Those are the endpoints of my interval. So if I take the cubed root of 0, we've already done that and gotten 0 out. If I take the cubed root of 8, again, that's my function, is the cubed root function. Cubed root of 8, of course, is 2. So my secant line, we can use the same idea here, use point slope formula. Y minus y1 is equal to m times x minus x1. So I have y minus, actually I could make this a little bit easier on myself here. Since it goes through the point 0, 0, I already know the y-intercept. It's right at 0. That makes this equation much easier. I'm just going to use this equation, y equals mx plus b. You could use the point slope formula, but since I already know basically the y-intercept and the slope isn't going to be too bad to calculate, it's going to be pretty straightforward. In fact, I already know the slope. Remember, the slope of my secant line is the same as the slope of my tangent line. My tangent line has a slope of 1/4, and we've already calculated the slope back up here, f of 8 minus f of 0 over 8 minus 0. That's the 1/4. So I have all the information I needed. I guess the only thing I really needed to do was find the y-intercept there, which was the 0. So we end up with y equals 1/4 x. So let's go ahead and graph these three functions here together. My original function, my tangent line, and my secant line. And we're hoping that we can show that, in fact, there is a parallel relationship between my secant and tangent line. So let's go to y1 and let's put in x to the, x raised to the 1/3. And let's put the tangent line in next. That's 0.25 times x minus 1.5396. And then add on the 1.1547. And then we'll graph along with that the secant line, which is 0.25x. And let's set up our window. Let's go from -1 to 9. I really only need 0 to 8, but I want to have a little bit of space on either side there, I guess. And let's go from -1. I know that at x equals 0, I get a y value of 0. And at x equals 8, I'm going to get a y value of 2. So I'm going to go from -1 to 3. Should give us a decent sketch of this thing. So there's our cube root function. There's our tangent line touching at 1.5396. And there's our secant line. Definitely looks like those two are parallel to each other. All right. Let's take a look at the next theorem here. The other theorem was called Rolle's theorem. And Rolle's theorem actually looks very similar to mean value theorem. In fact, the first two conditions here that you have to meet for Rolle's theorem are the same, actually, for mean value theorem. That's a nice thing. So the first condition here says is f is differentiable on the open interval from a to b. And we know that means you don't include the endpoints. And the second condition is that f is continuous on the closed interval from a to b. That means you do include the endpoints. And the third condition for Rolle's talks about those endpoints, that f of a has to be equal to f of b, which has to be 0. So in other words, your endpoints have to be x-intercepts. You have to cross the x-axis or touch the x-axis at the endpoint. So you can't just pick any interval here for Rolle's theorem. It has to be an interval that has x-intercepts at the endpoints. And then the conclusion is if you meet all three of those conditions, then there exists a point C on the interval from a to b such that f prime of c equals 0, which looks very similar to the conclusion of mean value theorem. It was f prime of c equals something. Here in this case it's 0. But if you look at f of a and f of b, both of those are 0. So it turns out if we were to calculate f of b minus f of a all over b minus a, we would get 0. So it turns out it's actually the same conclusion here. It looks like that f prime of c, the slope of my tangent line, is equal to the slope of my secant line. In fact, let's look at a sketch of this to help illustrate that. Again, when I sketch this function, I can't just pick any sketch of a function that I want. I have to be a little bit more careful because my endpoints have to be x-intercepts. So let me sketch a curve that does something like this maybe. So we'll call this A, and we'll call this B. And so we can see that we got differentiability on the entire interval. We've got continuity on the entire interval. I can see that at my endpoints here, that at A I've got f of A is equal to 0, and at B I've got f of B is equal to 0. Those are x-intercepts. So I meet all three conditions of Rolle's theorem. And the conclusion then is that f prime at C, there exists some point C, and I'm going to say that must be somewhere about right here, such that f prime at C has a slope of 0, which, like I stated, if we look at our secant line goes through these 2 points. Our secant line has that exact same slope. So again, you could state the conclusion the same way, that the slope of my tangent line, this here is my tangent line, is equal to the slope of my secant line. Just turns out to be that the slope of my secant line is 0 in this case. So that's what Rolle's theorem says. Now the reason that we have Rolle's theorem thrown into the mix here is because of the fact that in order to prove mean value theorem, we use Rolle's theorem. Rolle's theorem is a lot easier to prove by itself, and then mean value theorem becomes a lot easier to prove once we already know that Rolle's theorem is true. So that's the connection here. We use Rolle's theorem to help us prove mean value theorem, but by far the most important theorem, I guess, for us here is the fact that we know mean value theorem and the connection it's going to have. All right, so let's take a look at an example with Rolle's theorem. It says, given the function f of x equals x sine of x, find the first interval of non-negative x values on which the hypotheses of Rolle's theorem are true. So notice they didn't give you an interval. In fact, they're saying find the interval. And the reason why they can do that is because you have to pick an interval where the endpoints are x-intercepts. So I should be able to find that. Find the first interval of non-negative x values. All right, so let's first find that interval. And we're going to use our calculator to help us do that. So I'm going to get rid of these three functions here, and let's put in x sine of x. And they say the first set of non-negative x values, so that at least gives me a hint as to what interval, or at least I want to start with positive values in terms of my window here. So I'll go from 0. I know that at x equals 0, of course, I'm going to get 0 times sine of 0, which is 0. So I know I've got an x-intercept there. I'm not sure exactly how far to the right I need to go here, but let's just go out to 10 here. And we'll sketch this from -5 to 5 for our y values. That should give us a decent sketch of this graph. And last thing I want to check is make sure I'm in radian mode there for sine, and we are. And actually, that's a pretty decent sketch of this thing. You can see how you've got multiple places where it crosses the x-intercept, but they're saying to find the first set of non-negative x values where this happens. So in other words, I'm trying to find out, I know this endpoint right here is at 0. That one's obvious, but this one right here is the other one I need to find. That's my interval that I've got to work with. So let's use the calculator to help us do that. So again, you can check to make sure that, in fact, that you have an x-intercept of 0. When I plug in x equals 0, you get 0 out. The other 0, though, I'm going to use my calculator to help me calculate that. So we'll give it a left bound here. We're just going to calculate a 0. And give it a right bound, and we'll give it a guess. And it turns out it's at, oh, what do you know, 3.14. That's pi. Okay? So it looks like the interval for us to work with here is from 0 to pi. Which makes sense there that when x is equal to 0, sine of 0, of course, is 0. And then pi units later at x equals pi, sine of pi is 0 again. At 2 pi, it'd be 0 again, and so forth. Okay? All right. That's the first part of the question. Then it said, then find the point x equals c in which the in the corresponding interval at which the conclusion of Rolle's theorem is true. And illustrate this with a graph. Now, they didn't ask us to prove that the conditions are met, so I won't worry about that in this problem. But if they did say that, then I'd have to go through and show why I meet all three conditions. So for this one, I just need to find this value of c from the conclusion. Remember, the conclusion is that there exists a point c such that f prime of c is equal to 0. So I need to find the derivative of my function. In fact, I'm going to just slide this down here so I can find the derivative up above here. So I know that f prime of x is equal to, now this is a product, so we've got to follow product rule. Derivative of the first function is 1 times the second function plus the first function, x, times the derivative of the second function. Derivative of sine is cosine of x. And so there's not much I can do with that. I'm going to just leave it as is. But I can now substitute that into my equation that I have here. Now, if you want to leave this in terms of x, that's fine to do so. If you want to put it in terms of c, like we have written down here, f prime of c, that's fine as well. It doesn't matter to me which way you write it, whether you say f prime of x equals 0 or f prime of c equals 0. I'm going to go ahead and write it in terms of c just because that's the way I've gotten written here. But replacing c, my x's with c's then would give me sine of c times c, or excuse me, sine of c plus c times the cosine of c. And I want to find out where that's equal to 0. That's an equation that you're not going to be able to solve algebraically. We're going to have to use our calculator to help us do that. So I'm going to just go ahead and graph this derivative function and set it equal to 0, find out where it crosses the x-axis. So let's go back to our graph. I'm going to go ahead and shut off the first function. I don't need that here. And it's going to be the sine of x plus x times the cosine of x. Oops. All right, and we just want to graph that and find in the interval from 0 to pi where this is equal to 0. And so I'm going to just change my window to go from 0 to pi. If you want to see more solutions of it, you certainly could, but I really don't care to see those or don't need to see those. I just really need to see where this thing is equal to 0 from that in that interval. So we'll sketch just from 0 to pi. And I see actually there's two solutions here. You can see that at x equals 0, it looks like If I trace this at 0, it looks like at x equals 0, yeah, I have a y value of 0. But remember, the conclusion is that there exists a point C in the open interval. So that means not including the endpoint. So I can't use this endpoint. Can't use either endpoint. I have to find that point that's in the middle of my screen there. So let's see if we can find that one. So let's calculate that 0. And we'll give it a guess here, somewhere about right there. Looks good. Somewhere around 2 here is what I'm looking at from my tick marks there that are on the screen. But let me see what value it turns out to be. It's 2.0287. 2.0287. 2.0287 is the value that we got there. All right, so there's the question they asked us to find that value C. Find the point x equals C. And then it says finally illustrate with a graph there. So if you were to go back to the original sketch, let me go back to my original function. And I'm going to save this value of x. That's the last value it calculated. I'm going to go ahead and store that into a variable here so I can come back and use that. I'm going to store it into A. When I regraph this, it's going to change the value of x here on me, so I won't be able to use that value. And you can see that I hit this maximum here somewhere around 2. And if I calculate where that maximum's at, and the maximum somewhere around here. This is my original function. My maximum turns out to occur at, oh, what do you know? X equals 2.0287. That's that value that I just came up with. Okay? The slope at that maximum point there is 0. That's what the conclusion of mean value theorem guarantees me. There's a point C such that f prime at C has to be equal to 0. All right, and that's the end of our discussion here for this part of the section.